now that we have defined probability mass functions and distribution functions, we have some capability of making use of the randomness. In this video, I will be describing expectation and variance, and I'll try to introduce how we make use of them for making estimations in terms of particularly for machine learning. So let's give the title expectation. Other term for this is the expected value. But before I start introducing the mathematical definition, I would again like to invite you to think about a random variable as the lottery ticket that I'm holding in my hand. So random variable is an experiment. We don't know the outcome, but we would like to predict the future, right? We would like to at least associate one value that we can make use of it, right? So the lottery ticket, whenever say my mom purchases one lottery ticket, she thinks that the expected value for this lottery ticket is $1 million, because she thinks that she knows that she can, in theory, win $1 million, but what exactly is the expected value of this ticket? Obviously, this ticket is a random variable. It's not worthless, but it's not $1 million today before the outcome is known. So today it is one lottery ticket. Let's say, so this is my ticket, and I have my random variable in it, x. So this x can be of course $1 million here, but with some probability, right? So it has $1 million probability with this probability, and with some probability it can be $1. So it can be $1, and it can also be $0, right? It can be, I don't know, $10 too, like depending on the game. So we know with the associated probabilities as dictated by the probability mass function, probability density function, aka the distribution p of x, we can associate values for that. So how we calculate the expected value for a random variable with this E operation, and E operation is called the expected value of this random variable, that's going to give us one value, one real number, and this expected value is for us to make use of this randomness. So so that we can do useful actions, right? So that's what we want to do. An expected value of this random variable is calculated over all of the possible values that x can take, and over these all possible values, each of these x's will be considered. $1 million is in here, $1 is here, 0 is here, and multiplied with its probability. So this formula is our expected value. Similarly, for continuous random variables, it is defined in a very similar way. So let's call it for discrete. For continuous random variables, you guessed it, it's no longer summation, it's an integral x dot px dx from minus infinity to infinity, and this is for continuous. So this is the expected value. So if the expected value of the lottery ticket is more than $1, it's reasonable to pay $1 for this lottery ticket. But obviously, you know, that it's not the case. Otherwise, how would the people who organize this lottery be able to print out and create this thing? Obviously, the expected value before you purchase the ticket is less than $1, such that by you paying, along with everybody else, paying $1 for each and every one of the lottery tickets, house always wins, right? So that's the expected value. So you can see the expected value of one random variable as the mean of it, right? You can also try to try to observe the same thing with different experiments. So let me try to write the randomness in other way. So let this axis be the set of experiments that we can have, and let's say we are observing the x values. Obviously, the x value with every different experiment that I will observe will be different for a random variable, right? So I will observe this number first, and then it can be this, it can be low, something like this. So I can have something that might look like noise to you, right? So this can be a random variable, right? Because the outcome is random, and we can taking care of looking at every single outcome during my random experiment. I can build understandings of the statistical behavior of this random variable. First things, we know this. Let's try to draw the probability distribution of this thing, of this random variable, that over some topic that we have discussed, which is the probability density. If we could look at this graph by tilting our heads to the side and valuing this axis, meaning the x-axis, and if we could project all of the outcomes on this axis, we would very much be able to draw the distribution, right? So we can call this p of x, right? And all of our observations will be around one number, and this number will be on average somewhere in between the maximum and minimum values of the observables, and we can talk about this to be the expected value. There's one other term for this. We also use the letter, Greek letter m, meaning the mu, to demonstrate the expected value of this random variable. And you notice that there's one other thing that we should be aware of when we're calculating, when we're doing some action planning for the randomness. So we know on average what we would expect for this random variable, and that's the expected value. And there's some other limit that we would want to observe, and that's how much it deviates from the mean, right? So this sentence, I'm gonna try again, the value, the degree of how much it would deviate from the mean. So we would like to have some understanding of this random variable deviating from its mean, x minus e of x, and we would like to have an expected value of this thing, how much it deviates. Obviously, whatever we observe can be greater or less than the expected value, so we would want to take the square of this one to be able to measure how much my distance is. And as you see, although this e of x is a real number, this x is a random variable. So this random variable is already random, it's not a number. And one way for me to measure the randomness, the expected value of this random number, which is also a random number, is to take it inside one expected value, right? So I'm gonna, when you look at this equation, I'm going to read it as if I'm reading an English sentence, so that it's meaningful to us. So this is an expected value, how much I expect this random variable to diverge, to vary around its mean. And there's a name for this thing, and this thing is called the variance, right? Sigma square x, and this is pronounced variance. Variance helps me understand how much it varies, how much my random variable varies around its mean. But note that its units is going to be square of what the actual observable's units, right? So if my observable is seconds, how many seconds would I expect blah blah to happen? How many volts? How many milligrams? Blah blah. The variance unit will be square of it because of this little square here. That's why many times instead of the variance, we value the square root of this expectation, which is just the sigma of x, and the sigma is the Greek letter x, and the sigma of x is referred to as the standard deviation.